Hello everyone. Let's begin with a thought. Have you ever wondered how physics allows us to compare such different things, like the speed of a car, the force of a kick, or the energy in a moving ball? Behind all of this is the idea of dimensions. Dimensions express any physical quantity in terms of three building blocks: length, denoted by L, mass, denoted by m, and time, denoted by t. For example, velocity is simply distance traveled per unit of time. Whether you measure it in meters per second or kilometers per hour, the underlying dimensions remain the same. So dimensions are not about the chosen units, but about the fundamental nature of the quantity. They act like the universal grammar of physics, letting us connect, compare, and even check the correctness of equations. Let's make this concrete. Velocity is defined as displacement divided by time. In formula form, v equals delta x divided by delta t. Displacement has the dimension of length, written as L. Time has the dimension t. So, velocity has the dimensions L raised to the power 1 multiplied by t raised to the power minus 1. We write this as L to the power 1, m to the power 0, t to the power minus 1. This means velocity depends on length and time, but not on mass. And as you can see in the diagram, if a car moves a distance delta x in a certain time delta t, velocity describes the ratio, regardless of whether you measure it in meters per second or kilometers per hour.
Now here's the general rule. We write the dimensions of any quantity in the form L raised to the power a, m raised to the power b, t raised to the power c. The values of a, b, and c can be positive, negative, or zero. Take force as an example. From Newton's second law, force F equals mass m multiplied by acceleration a. Mass has the dimension m. Acceleration is velocity divided by time. Velocity is Lt to the power minus 1, so acceleration is Lt to the power minus 2. Multiplying mass m with acceleration Lt to the power minus 2, we get the dimensional formula of force as L to the power 1, m to the power 1, t to the power minus 2. This means force depends directly on mass and length, but inversely on the square of time. Why are dimensions so important? First, they give us a universal way to compare quantities across physics. Second, they allow us to check whether an equation is correct. For example, if the left-hand side and the right-hand side of an equation do not have the same dimensions, then the equation is not valid. Third, dimensional analysis helps us derive relations between physical quantities, even when we don't know the exact formula. And finally, it helps us convert between unit systems, like from SI to CGS. So, dimensions are not abstract symbols. They are practical tools that keep our physics consistent and reliable. Let's quickly go through some examples. Acceleration equals change in velocity divided by time. Its formula becomes Lt to the power minus 2. Momentum equals mass multiplied by velocity. That gives mLt to the power minus 1. Energy equals force multiplied by displacement. Force is mLt to the power minus 2 multiplied by length L. So energy becomes mL squared t to the power minus 2. Pressure equals force divided by area. That becomes mL to the power minus 1t to the power minus 2. So, with just three basic dimensions, length, mass, and time, we can represent a wide variety of physical quantities. Now let's solve an advanced example. The dimensional formula of the universal gravitational constant g. Newton's law of gravitation states force F equals g multiplied by m sub 1 multiplied by m sub 2 divided by r squared. Rearranging, g equals F multiplied by r squared divided by m sub 1 multiplied by m sub 2. Now substitute the dimensions. Force F is mLt to the power minus 2. Distance squared is L squared. Mass squared is m squared. So g equals open bracket mLt to the power minus 2 close bracket multiplied by L squared divided by m squared. Simplifying gives m to the power minus 1, L cubed, t to the power minus 2. Therefore, the dimensional formula of G is L to the power 3, m to the power minus 1, t to the power minus 2. As shown in the diagram, two masses m1 and m2, separated by distance r, exert a gravitational force on each other, and G is the constant that governs this universal attraction. Let's quickly revise. Dimensions break every physical quantity down into the basic units of length, L, mass, m, and time t. Velocity is Lt to the power minus 1. Force is mLt to the power minus 2 Lt to the power minus 2. Energy is mL squared T to the power minus 2. And the gravitational constant G is L cubed m to the power minus 1T to the power minus 2. Dimensions allow us to check equations, convert units, and even derive relations when exact formulas are unknown. They are the grammar of physics, ensuring that every law makes sense. I hope this session gave you a clear and deep understanding of dimensions. In the next topic, we'll see how dimensional analysis can be applied to real problem solving. Until then, keep observing the physics in everyday life.